No. Okay. Thanks again for your presentation. And we will move on to the next one, whose paper ID is 341, Dr. Lou Draganov. He is an associate professor in radio communications and radio technologies department at Technical University of Sofia, Bulgaria. He teaches multimedia systems and digital video broadcasting, as well as other subjects to both undergraduate and graduate students. He wrote more than 80 papers and participated in numerous national and international scientific projects. His main fields of scientific work are digital image processing, pattern recognition, neural networks, and multimedia systems. He is a member of IEEE. The speech title is Optimizing the Non-Local Means Filtering of City Images. Dr. Lu, please share your screen.
Thank you.
Hello.
Hello,
After you.
can you hear me?
Yes, you can cancel your virtual background because
Okay.
yes.
Thank you. I'll present to your attention my paper entitled Optimizing the Non-Local Means Filtering of Computed Tomography
我
Images.
知道，但是我怎么矫正你是可以。
Can you see my presentation?
Yes.
Thank you. Thank you. So, computed tomography images play a crucial role in the medical diagnostics. Some of the recent approaches which aim to enhance the quality of CT images are included into our research. In the first place, the work of Zhang and al. Include adaptive non-local means filter with local principal neighborhoods. Using this technique, the authors retain the structures of the organs from low-dose computed tomography. They achieved root mean square errors of the filtered images in the order of 1035, while the non-local means filter alone achieves only 13.53. Another work of Zhang and co-authors used the combination of tensor decomposition and non-local means, which decreases the extremely high levels of noise into the spectral CT. The root mean square error here is in the order of 0.225 inverse centimeters up to 0.0217 inverse centimeters. The structural similarity index varies between 0.633 and 0.987. In another research, Chen and co-authors apply high-definition neurovisualization technique of a rodent brain. They use the ex vivo method and the non-local means filtering for the 3D images, achieving a detail in the picture comparable to 4-point light micrographs. The resolutions at which this is achieved is up to 2 to 3 micrometers per voxel, and the scanning time is above 15 hours. The authors achieve satisfactory levels of the signal-to-noise ratio. Bao and co-authors use the multi-scale transform and the non-local means, which are used for denoising of positron emission tomography images. Positive results have been reported from these tests, and this approach has this additional benefit of increasing the contrast of the filtered images. Alantari and co-authors use the non-local means filter for denoising high and low energy images obtained from dual energy X-ray absorptiometry. The SNR here for the high and the low phantom images increases respectively with above 30 and 27%. Juma and co-authors use multi-scale transform and the NLM filter for denoising PET images, as in the previous study, and they have noise levels of around 7.68%. The chi-square parameter, which is the evaluating matrix here, is in the order of 4. The peak signal to noise ratio they achieved after filtering is around 74 decibels, and the structural similarity index measure is in the order of 0.27. Panigrahi and co-authors use the multi-scale NLM filter using a curvelet transform and hard thresholding. The PSNR for noise level of 40 for the standard deviation is around 29 decibels. For the LLM filter alone, this is around 27. The SSIM is 0.77, and this composite technique proved quite efficient employing the NLM filter. Kim and co-authors filter CT fluoractic images denoised by the NLM in fast implementation. Their achieved value for PSNR is 82 decibels, and the contrast to noise ratio is in the order of 236. Shim and co-authors propose the same fast technique in order to detect pulmonary nodules. The coefficient of variation reaches here above 2.5, and the contrast to noise ratio is around 22. The last work which we investigated prior to carry our tests includes the adaptive NLM filter over basis material images obtained from dual energy CAT scans at low emitting dose. Depending on the type of the basis material and the dose level, the PSNR here varies between 20 and 31 decibels. Large variety of implementations exist for the NLM filter, and the different combinations with other techniques. In most of the cases, all these are adapted for particular purposes, while the main goal of our study is to propose a general scheme for optimizing the main parameters of the filter over CAT scans. As we shall see, this leads to optimal results of defiltration. In equation 1, we could see the general formula for the non-local means filter. It uses a window of averaging values, which is being compared to other windows around the same area into a search window, and thus producing weights which are used for each of the pixels into the comparison window, which further on after the weighting process are being averaged. The weights themselves need to satisfy the condition from equation 2. The overall sum of them is 1. And the weights themselves could be estimated, as it is shown in reference 11, using equation 3. It's a nonlinear exponential function which has this control parameter h, which is the degree of filtering. Basically, this is a comparison between the central pixel into the comparison window and adjacent pixels around that window. So this parameter is one of the point of interest in our study, how we can actually get its optimal value. We could see also that for the comparison, actually two comparison windows within the image, assuming that the noise present is equally distributed all over the image, equation 5 becomes a helpful reference in order to find approximately as a prognostic value the standard deviation of the noise in the image. We could see that on the right side of this equation. The comparisons made within the search window with the biggest size with S by S pixels is we need to know how big this window should be, what is the optimal value of S. And the third parameter which we investigate is the size of the comparison window where the actual equation of the filtration takes place. This is the optimization procedure which we propose for that purpose. We start with a noisy image IN after adding additive white Gaussian noise and initialize the degree of smoothing, the search window, and the comparison window, all three parameters equal to 1. Then we perform the non-local means filtering and estimate the peak signal to noise ratio and the structural similarity index. Then we continue with incrementing sequentially the size of the comparison window by 2 pixels each time. It is 2 because we need to have odd number of pixels over each dimension. So starting with 1, we would sequentially have 3, 5, 7, and so on. And the same is the situation with the search window. We use increments in 2, but the upper bound for the search window is set to 43, while the comparison window reaches only 11 by 11 pixels. The degree of smoothing is being changed with increments of 1000 from 1 to 65,535, which is the upper possible intensity of the CAT scans that we are dealing with. For all the combinations between CS and DOS, we estimate PSNR and SSIM each time. And finally, at the end, we find the maximum achieved values from which the optimal CS and DOS are derived. The image test set we use is an excerpt of the deep lesion dataset. It includes 103 CAT scan images. Their dimensions are 512 by 512 pixels at 16 bits per pixel. And below is shown the testing platform that we use for the purpose. We are working with 3 levels of additive white Gaussian noise. There are 1000 of the unit, 100 of a unit, and 1/10 of the unit for the variance of the noise. On figure 2, we could see how the PSNR and SSIM are changing with the increase of the degree of smoothing. And as the graphs clearly show, we have a saturation area above DOS equals 19,000. We think that further increment of DOS is not necessary. We have the peaks for both these parameters there, and 19,000 is the optimal value for DOS. In the same time, the change of the PSNR and SSIM with the change of S and C is shown on figure 4. Here we have again a saturation area, this time in 3D, since we have two independent variables. And the optimal value to which we get the maximum PSNR, the maximum SSIM are 5 for C and 43 for S. Of course, with the increase of the comparison and search window, the processing time increases. This is shown on figure 5, as we can see almost a linear uprise into that time. Once we find the optimal S, C, and DOS, the processing time of all images we have regarding the DOS change could be seen on figure 3. We've done this experiment in order to show that DOS doesn't actually affect the processing time from a standpoint of its value. We have a steady average value of around 0.18 seconds for each of the images which are being processed. Only S and C actually affects the filtering time. These are the quantitative results in table 1 from filtering all 103 images. For the lesson noise, we have a PSNR of around 47 decibels, more than 17 decibels than the Gaussian filter, which is very popular in the field, and around 10 times more than the average filter with its simple box shape transfer function. The structural similarity is quite high, 0.9954, more than half than the Gaussian filter and close to the average filter. The actual disadvantage of the NLM filter in its optimal configuration is the higher processing time, which is at least 2 orders of a magnitude higher than the Gaussian and the average filter. The tendency in beta filtration is preserved with higher level of noises. For 100 and 1/10 of the unit for the variance, we have around 20 times 20 decibels and more for the NLM filter than the Gaussian filter. And this proves its steady operation with this optimal configuration we get. On figure 6, we could see a sample image, the original in A. B is the noisy image at 0.01. C is the result from the Gaussian filter. And on D, we see the result from the average filter. The optimal NML filter is on the right upward corner in E. And as the figure clearly shows, we have quite a significant degree of smoothing with removing most of the grainy structure of the overall content. It's worth noting that these images here are being downscaled to 8 bits per pixels, since we cannot see 16 bits per pixel on the screen, but nevertheless, they are quite indicative. As a conclusion, we could say that the general optimization scheme, which is proposed here, could be applied in numerous instances for filtering also other types of images. The experimental results show that the degree of smoothing affect the quality, and the increase of that parameter leads to maximum achievable PSNR and SSIM. The minimal value for which this happens could be found, and this is one of the optimal parameters from the optimization procedure. The change of DOS has no significant effect on the filtration time. The sizes of the search and the comparison windows have a non-linear effect over the quality of the reconstructed images. For both of them, there are saturation areas from where we get the optimal values. The computational time increases monotonically with the increase of the surface of the search and the comparison window. And the NLM filter provides better quality of the filtered city images than the Gaussian and the average filters. The filtering time of all three filters does not depend on the noise level, while the NLM filter is 2 orders of a magnitude slower than the other two filters. As a future work, we think of finding an optimal configuration, actually optimized configuration of the NLL filter in terms of the processing time, since now it's considerable duration taken for the filtering. And also we intend to test it with other types of images, such as magnetoresonance images, multispectral, and hyperspectral images. Thank you for your attention.
Thank you, Dr.